All right, so here we are. Part 3 of our trilogy of how did Newton figure this out anyways? It's unbelievable. We started off talking about Johannes Kepler and Kepler's 3 laws. We then looked at how Newton came up with a thought experiment about satellite motion, saw the connection between the apple and the moon, and finally recognized the inverse square law. The fact that the force of gravity is related to 1 over the distance squared. Now, as we move on to the next notes, you don't need to write this, but here it is. So to get us up to speed, we got to tie this all together. And that's what Newton's 3 laws do. Now, you can see in the notes that I have right here, got to go back to the inverse square law nature of gravity, that the force is proportional to 1 over r squared. That was his key insight into how the force of gravity works. Now, what I would like to do is to look at how Newton's 3 laws support and explain the universal law of gravity, which, as you can see, I have written here for the first time, F equals G m1 m2 over r squared. And trust me, we'll do a lot of problems with these, so relax. We'll write this down many times. I will say one thing before we begin, that G is a fundamental constant of the universe that has to do with things measured in newtons, kilograms, and meters. If you understood that, that's really impressive. Right now, what I would like you to do is to take out that sheet that says Newton's 3 laws, if you would, and let's pick up our story there. Back when we first talked about Newton's 3 laws, I made a point of stressing to you that they're not as simple as they seem at first. In fact, it's the reason we even study Newton's 3 laws is not for our earlier idea of making sure we understand inertia and F equals ma, although that's some great quantifying of problems. What Newton was really doing was setting the stage for gravity. And in hindsight, when we look at all of his work together, it makes beautiful sense. So here it is. While home from Cambridge University in England, at the age of 21 or 22, where he was a student, Newton developed the ideas that finally coalesced into his famous universal law of gravitation. With this masterpiece, Newton was able to explain one of the questions that had gone unanswered since the beginning of human civilization and the first time modern man, or humans, looked up at the wanderers, the planets. How did he do it? He started off with his equally famous 3 laws of motion. Let's look at how this applies to gravity. Here we go. I took the liberty of drawing in a circle, so it would look nice to start. The first law of motion was actually developed by Galileo Galilei. But Newton did a better job packaging it all together, so we call it Newton's first law. And if you feel the urge, go ahead and recite it with me as we go. An object at rest stays at rest. An object in linear motion stays in linear motion until acted upon by an outside force. Now, Kepler, as we discussed, had gotten rid of the idea of the planets traveling in a perfectly uniform circle. That was no longer considered a natural state of being for an object is to continue in a circle. What Newton is saying with his first law is that if an object is traveling, it will continue to travel in a straight line unless there is a force acting on it. Basically, what he is saying is that the planets are orbiting our sun because otherwise they wouldn't orbit unless there's a force of gravity acting on them. So essentially, it established the need for the force of gravity. Newton's first law, law of inertia. If the planets are traveling in roughly circular orbits, there must be a force acting on them. Now, Newton's second law, we're going to come back to in a moment. Newton's third law is actually the other piece of the puzzle when it comes to how did he know what that formula was. Okay, so here it is. Here's the Earth. orbiting our sun. And how does that play into Newton's third law? Let's take a look. When one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. Wait a minute, huh? Let's try that again, but instead of when one object, let's use the word Earth and Sun. When the Earth exerts a force on the Sun exerts an equal and opposite force on the Earth. The force of gravity is not just on the Earth, but there is also a force of gravity on the Sun, and those two values are equal. Now, mathematically, how am I going to end up with a value where the forces are equal? Well, let's look at it this way. I know that the force is proportional to 1 over r squared, but that doesn't take into account the mass of the objects. What if I take the mass of those objects and I multiply them times each other? The mass of the Earth times the mass of the Sun. Now, if I look at the force of gravity from the perspective of the Earth, right? It would be the product of the mass of the Sun and the mass of the Earth divided by the distance of the Earth squared. Or if I looked at it from the perspective of the Sun, it would be the same thing. Newton's third law is not about if I push this desk and the desk pushes back on me. It's about the planets orbiting the Sun. They both experience the same force. And the way for that to occur is to take those masses and multiply them times each other. That's it. Now, I have a formula here for the forces proportional to. In order to turn that into an equals, we need to insert a constant. So that constant, when it comes to gravity, is the universal gravitation constant. And we use the letter capital G for that. And that is how Newton came up with the universal law of gravity. The inverse square nature and Newton's third law. We'll come back to G in a bit. Just so you know, G is a value that's been determined to be 6.67 times 10 to the negative 11. And that's Newton meters squared per kilogram squared. We'll come back to it. No need to stress, it's just a constant. A universal constant. Everywhere, it's the same. Now, oh wait, we just did it. We just did it like that. We just showed where the universal law of gravity came from. But how do we know that's not just some letters? That's where Newton's second law comes into play. So, Newton's second law we spoke about at length earlier when we were doing our best to show that motion can be quantified. F equals ma, the sum of the forces, causes the mass to accelerate. Now in this case, because the planets, that force is perpendicular to the velocity, the sum of the forces is going to cause the mass to go in a circle. Now gravity does not always make things go in a circle. Gravity acts in a straight line. But if one of the objects is already moving, then it can go in a circle. Okay? Now, the force that he is talking about is the force of gravity. G m1 m2 over r squared causes mass 2 to go in a circle. See, what I did there was I just made m2, the object that's accelerating, the orbiting mass. That's the one that has the acceleration in this problem. Okay? So for a planet, that would be the mass of the planet. Yeah. All right. So let's take it one step further. Let's take it a few steps further. Let's say if I were to rewrite that as G m1 m2 over r squared causes mass 2 to go in a circle, I can start doing some algebra and crossing things out. Go ahead. Feel free to go ahead of me. Mass 2 is going to cancel out. R is going to cancel out. And what I'm going to end up with is Gm over r equals v squared. Now this mass 1 for the planets orbiting our sun, I'm going to let that be m subscript s. No big deal. Wait, how does this prove anything? This doesn't prove anything at all. But wait, if we substitute in for the velocity 2 pi r over the period, we take that quantity and square it. Yeah, because the planets are going roughly in circular orbits. I'm going to take those values and square them up. Let's do it. Good. All right. And then to clean this up, I'm going to get it all on one line. So G, mass of the sun times the period of the planet squared equals 4 pi squared r cubed. Do you see it? Do you? Some of you see it. This was 1664. He claims to have come up with this. Yeah, I know. It's amazing, isn't it? Right here, this proves that the universal law of gravity works when we discuss the motion of the planets around the sun. Because watch, if I get period squared divided by the radius of that planet's orbit cubed equals 4 pi squared over g times the mass of the sun. Yeah, that look familiar? Johannes Kepler, 40 years prior, had derived a formula from data that period squared over r cubed was constant. And if we look at our formula for that we just derived from theory, no data, we end up with period squared over r cubed equals 4 pi squared times the universal constant g times the mass of the sun, which for the planets that are orbiting our sun, it's all going to be the same. So Newton's new theory of gravity exactly matched the result that the greatest mathematician of the night sky had derived from data 40 years prior. And that's it. That's the proof that is needed to show that the universal law of gravity is real, that it really does describe the motion of the planets around our sun. That's it. He came to the same result as Kepler. Just for him, it all came back to the sum of the forces causes the mass to accelerate. And everything else, you just understood. Now, I highly encourage you to go and explain this to your younger sister. If she's smart, go for it. You could explain it to your older brother, unless he's not that smart, then don't. You could explain this to your parents tonight. This is one of the fundamental findings of human civilization, is we explain how the planets orbit the sun. And you just followed it. That's pretty good. Good for you. I hope you get it. We'll talk more about it in a bit. Trust me, we're going to do a lot of different problems with it. But I think it's important as a human being that you understand where this comes from. And not only that, that you can understand it. And